blade element theory, because earlier we related the thrust, the inflow and the power, rotor disk area only induced using momentum theory, but that does not consider any detail. But now we are going to look at the details of the rotor operating condition, everything. But that is the blade element theory. Please understand, this is a fundamental. We have to have this theory for all analysis of helicopters, and whether it is flight dynamics, whether it is aeroelasticity, loads, stability, everything. Blade element theory is the fundamental. So, you have to know the blade element theory, but to give you a brief history, see, it was proposed by, he basically started William Froude in 1878, because blade element theory essentially says that I am going to treat every cross section of the blade, because you know that the rotor blade is essentially a, if you look at that, this is a airfoil shape. Okay. He said I am going to look at the cross section of the blade, which is an aerofoil, because these are all, please understand, before the flight started, even the fixed wing. But then the real development was done by Stefan, you pronounce it Drevicki or something, it is 1892 to 1920. What he did was the propeller, these are all for propellers. As the propeller is going forward, it is not hovering, there is a velocity which is coming, okay, and there is a omega r, which is due to rotation velocity at any cross section. But he did not take into account the velocity due to the inflow or the induced velocity. He just took the propeller forward velocity and then the omega r, and when he calculated the thrust, the power, etc., it was not matching with the experiment, because please understand, propeller experiments were, lot of experiments were conducted earlier for power and thrust, and he found that they were not matching, because then he felt there is something wrong between theory and experiment, and the difference, he thought it is due to the aspect ratio of the, basically the propeller, because it is not a long propeller, it is a finite propeller. But he was not sure what is the aerodynamic characteristic I must take into account at every section. So, when he made some correction for aspect ratio, because you know that there is a correction for aspect ratio in the finite wing theory. Similarly, when the trends were okay, but still the results are not good, they are not matching with the experiment. Then several people attempted to see how to take the proper sectional characteristic, because you have two, one is the aspect ratio effect, okay. Another one is airfoil characteristic. Okay. These are the two things. There is something I have to make adjustment. Okay. So, in 1915 and 1918 and also 17, that is Betts and Bothesat, and then Page and Collins. See, these are the three group of people. They said I have to take the induced velocity. Okay. But what induced velocity I should take at the, if I want to calculate the lift here, the propeller, this is going, this is the cross section, omega r is there. Okay. So, you may take, this is my omega r, and there is a propeller is going, axial velocity of the propeller, which you may call it v, plus some induced flow. Okay. They said we will take the induced flow from momentum theory or something like that, but still, but it is not aspect ratio effect, they started using it. So, you have an aspect ratio effect was also brought, but you took the inflow also, again there was a mismatch. So, they found that there is something wrong, in the sense something inflow, if I take it from momentum theory, if I take the aspect ratio, they do not match, again they give a trend. So, they try to adjust some empirical numbers, that is why Page and Collins, he took the aspect ratio as 6, fixed the number, and then he started correcting the inflow by some empirical factor. Okay. This is how it was going on to match the theory experiment, purely thrust and power, that is all, nothing else. But later, because Prandtl finite wing theory, that is the Prandtl vortex, lifting line theory, that was in 1918 when he proposed. Then they said, yes, we have to, this is the vortex model, because I should take, lift is rho u gamma and the gamma is the vorticity, and you find out the strength of the gamma from actually the trailing edge, because you have to adjust. Lift you say rho u gamma, and then you go back and then take a vortex, finite horseshoe vortex, okay, and then get the strength of the vortex, then you use it. Then they said, yes, we have to use vortex theory to get the proper value of inflow at the place where it is going at the rotor disc. That is why in the beginning the correct treatment of 2D aerofoil theory for rotors came from vortex theory, because 2-dimensional there is a correction, because the vortice is given induced velocity, that is what you get a induced drag in your fixed wing theory. Okay. So, the vortex theory was dominating in the beginning of the rotors, because they said that is the correct treatment. So, everything went in vortex theory approach. Momentum theory was not really looked at, but subsequently then people realized, yes, you can take momentum theory, okay, and then make. But even today, if you want a more precise treatment of induced flow at the rotor disc, induced flow, I mean you all know that the flow normal to the rotor disc. If you want to get a correct value, because correct is something, exact is different, there is a vortex model, but that is more complex. Okay. Because if you start looking at the vortex theory as such, if I draw this as the rotor, this is a shaft, this is a rotor, it is rotating. Okay. Okay. This is the shaft. The vortices will be, because as it goes you will find a vortex coming, and if the lift is varying along, you will have a vortex sheet actually. Okay. A sheet will come, because this is a lifting line theory. I hope you understand, some of you may not know lifting line theory. Okay. Okay. And then the strength of the vortex, that varies how the lift variation, And then what is the shape of, because this is going to go in the rotor, it will go in a helical shape. Okay. Because in the finite wing case, you will say my vortex sheet is going like the horseshoe vortex, because this is what you say. This is a horseshoe vortex in finite wing. The vortex swept back. But in the case of rotor, hovering rotor, the vortex is piling below it. It will go in a helical path, because as it goes around it leaves, and this one pushed down by the induced velocity by its own traction. Now the structure of the vortex, you have to make approximation, because if you experimental observations were made on how the vortices look, and they found it goes in some kind of a, I will show later some pictures, okay. It will be like this, okay. So like that this will go, vortex sheet, and this, what will happen is initially they will start a sheet, suddenly they will all bunch up, become a tip, strong tip vortex, because you know that strong tip vortex and how that is convected down. That means you have to take a structure of that, that is the wake structure. Now that you have to know, or you say if you have vortex to vortex interaction, if you consider, then it is called the free wake theory. But if you say I fix my structure of the vortex, it is going to be in a cylindrical, vertical cylinder, that is all, no deformation, then I call it prescribed wake. So either I prescribe the wake structure, that is relatively easy, but if I do not prescribe, I say okay, let it evolve by itself, that is the free wake theory, but it is more complex. Even prescribed wake, free wake, both are complex. Now of course people have developed their own computational codes using vortex theory. Today I am telling you vortex theory is there, it is used, but the beauty is, if I consider a hovering rotor and then you assume that the vortex is in a cylinder, okay, and it is a infinite number of blades, actuator disc, okay, that means it is just a lot of circular continuous vortices, okay. It is easy for integration, that was what was done earlier. Cylindrical wake structure, and infinite number of blades means there is no gap between one and the other. Please understand, one blade gives a wake, it will come down, then there is another blade that will also give, that means there will be several helical wake and there will be gap between those wakes, because you get one coming down, then if you say another blade end, that will come and they will go intertwined. But if you have infinite number, it is almost like a continuous cylinder. When you use a cylindrical wake like this, the induced flow calculated by this approach at the rotor disc is same as momentum theory, okay, uniform loading, okay, uniform thing you take, then you get the same result. So what happens is, okay, momentum theory is not all that bad, alright. So we use in this course momentum theory. Please understand, momentum theory is even today in research it is used, okay. I will show you later how we use it, because if you want to have vortex theory, then you need to sit and develop. This is like a pretty much computationally more intensive, whereas you will find even with the momentum theory, the results which you predict are reasonably good. pretty good I would say, but you have to make some corrections here, there, etc. With that your results will be good, and that is why momentum theory is still used in rotor analysis. This some people may use it, that is a different point. It is then a school of thought, and if you want to complicate it, but it does not mean that everything you are able to predict, because the wake structure, unless it is correct, and you do not know, because the viscosity will diffuse the wake, how far you must go down. So, there is one group of researchers working on wake, that type of prescribed wake, free wake analysis. Another group, they said that okay, I need an inflow, because now you see the research itself was directing towards whether modeling the inflow accurately, that is the research. I do not do anything else except my focus is inflow modeling. How do I know what is the velocity at every point on the rotor disc? Even today it is a research. Later you will find how that itself gets complicated. Another one is, I have a good theory, pretty decent, which is easy to incorporate in my aeroelastic loads response analysis, because I need to do that also. So, you see the research, if somebody focuses on only aerodynamics related problems, he will be focusing on only that inflow calculation, he may not get into rest of the things. But if you are working on aeroelasticity, loads, stability, etc. of the vehicle, you need to know the inflow. You say I will calculate by momentum theory, which is easy to incorporate, but of course that will be somewhere, but it is not too bad, that is what I am saying. It still gives the results which are quite close, but of course there are always differences. Now one can debate on whether one should use always this theory or the other theory, then you will find slowly as we proceed, even that has certain drawbacks. Okay. Now I just gave a brief introduction with the field, how the research in inflow calculation is important particularly, but we will use not vortex theory, we will use simple momentum theory, but then we will complicate it, not the uniform inflow. That is what we did in the momentum theory. The flow over the disc is constant at every location, that is uniform inflow. Later you will see, hey, that is too gross an approximation, let me have non-uniform inflow. Okay. That means it is varying along the radial direction. Of course, if you want more complex in general various other situation, you can say it varies everywhere. Okay. So, that is how the complexity in the momentum theory also went up, and today that is also there. There is one theory which is a dynamic wake theory, which is somewhat similar to this, somewhat similar. So, please understand that model is what we use, dynamic wake. We do not model this, we use another theory to get the time varying inflow at the rotor disc. Please understand, we use till now constant, it does not vary with time, constant and uniform everywhere. Okay. Now you say initial development, we learned that it is a constant, it is uniform, first theory. Okay. That is what I am going to discuss now. Do not think that that is the end of it, because there is a lot more in the theory, in the inflow modeling alone. Okay. So, when we go to the research level, we do a little bit more complex thing. Okay. Now, what is the blade element theory? This is a rotor blade which is rotating. So, I said the cross section is this. I know what is the oncoming velocity. It is a 2-dimensional model, that is all, 2D airfoil model. There is omega r. Let us first consider hover and vertical flight. Okay. In the sense the disc can go straight up or down is a little, we will do that later. Vertical flight and up and down, that has its own complexities. Okay. We will do one by one slowly. Here I said that this is the rotor blade which is rotating with a angular velocity omega, and this is my frame x and z, and this is y which is attached to the blade, it keeps going. Now I look at a cross section which is at a distance r from the center of the disc, or you can say center of the hub, that is r. So your velocity is omega r, simple, because please note this is only an introduction. Okay. When you go to actual blade, it is not omega r alone, you have so many other terms will start coming in. So that is why when we start the course, you learn basics. Okay. And then at this is a small elemental cross section dr. Okay. Because please note my omega r is changing depending on the radius, that is why that lowercase r is used for running variable along the span of the blade. Now I have omega r, and I assume that this is the climb, you may put a subscript Vc to denote it is a climb velocity, and nu is induced velocity. You do not know that, but you say I know it somehow. You may get it from any theory. Okay. That is where you can use momentum theory, you can use vortex theory, etc. And that is why I marked up, which is perpendicular to the disc. So now I have a disc and this blade is going in the disc. Please understand, it is not coming out or anything like that. We will do later one by one. Okay. This is just a very simple theory. So this is rotating and there is a normal flow. So I have Vc and nu. Now if this is kept at a pitch angle theta with respect to the disc oncoming flow. Now you can get the relative velocity as well as the angle of effective angle of attack, you can say. So this is the phi. Okay. Phi is the change because of the normal flow. So you will have your resultant velocity u is okay. This is my resultant velocity, but for simplicity, you know, because of every time you do not want to carry this, you use the symbol up, that is the velocity perpendicular to the disc. This you call it as Vc plus nu, and u t which is omega r. This is tangential velocity, this is the normal velocity. Instead of calling normal n, you call it up. So, this is ut, this is up. Okay. This is a general symbol, this is a standard notation that is used so that it is ease of understanding. Ut is tangential, up is normal, only everything with reference to the aerofoil. Now, immediately you go back, what is my effective, because you know that tan phi is up over ut, tan phi is up over ut, and now I have to define sectional lift, sectional drag, that is all, and lift is normal to the, I use simple 2D aerofoil theory, lift is normal to the oncoming flow and drag is along the oncoming flow. So, now you see, and I define some psi just to denote the azimuth location. This is for one blade, if I have n number of blades, I will use all the blades, everything. Okay. Now, I got sectional lift and drag. Okay. This is for the, please note, very simple model, and this is what I have shown here. Okay. So, up, ut, and this is the resultant u, and theta is the pitch angle, and alpha is the effective angle of attack. Okay. So, you see effective angle of attack is what I, now you remember why I used pilot input gives pitch change, it does not change the angle of attack, it will change indirectly, but he gives only pitch change, in the sense he changes this angle, but the angle of attack changes depending on what is the up, what is the ut, etc. Okay. I may assume now this induced velocity nu to be constant over the rotor disc, that is, it is not a function of r, it is a constant, it is a hovering theory, it is hovering or climb, it is not a function of radial, it is a constant. Then you see the phi changes because of omega r. Okay. So, every cross section, because the tangential velocity is changing, so automatically my effective angle of attack, which I call it alpha, alpha is theta minus phi, which you may call it theta minus tan inverse up over ut, and then I am going to make approximation straight away right here. So, please understand, right at the definition of angle of attack you have tan coming in. Okay. You make now an approximation, because in a textbook form, if I have to give you a closed form solution, okay, computationally you can always take tan inverse, no problem, but you know that as r, this is nothing but what, V climb plus nu over omega r, as r decreases, this is very large, that means phi is going to become more and more as you come near the root. Okay. And that means the angle of attack, whatever you put, because this value will be drastically increasing. Okay, theta may be fixed, but this will keep on increasing, but then you are going to have problems. but usually what happens is your aerodynamic section, okay, starts not from the center of the hub. And another thing is the omega r, the dynamic pressure due to velocity, omega r is very small near the root. Okay. Therefore, you make an error, but you say it is all right, I accept that error. So, I represent this tan inverse, because I assume this angle is small. So, please understand, I assume phi is small, I write it up over ut, tan phi is phi. Okay. Tan phi is phi, when phi is small, up over ut, but I am violating this rule as I come closer to the hub, but I still say it is all right, I accept it, because I know that dynamic pressure is very low. So, the lift is not very large. So, I make, usually you will find the aerodynamic section of the rotor blade starts about 20-25% away from the center because of the geometry, because you have to have a hub, you have to have attachment, everything. So, it will be around 20%, 20-25%, and the error you make in that is not a lot. Okay. That is why you make this approximation first, theta minus up. Now, you know angle of attack. Okay. And I can write the lift per unit span, okay, straight from your aerodynamics. Lift per unit span is lift per unit span, please understand. Otherwise, over a small element you put a dr. You will have half rho u square card and CL. This is lift, and the drag will be, if you want to put, you can put a dr, okay, half, this is per unit span, this is the lift at CD, okay. This is my, at any small element. Now, if I want to get the total lift, I need to go and integrate, that is all. Now, I make more approximation, okay. The more approximation is, I am going to call now u, I say omega r is, because when phi is small, basically omega r is large. So, when omega r is large, this is a small quantity. So, I which is basically ut, okay. So, I represent my u as ut, resultant velocity as ut, okay, but that does not mean I change the angle of attack also, I keep alpha as this. Now, I know directly, I go back, I write my lift as half rho ut square, this is an approximation I am making, okay. And C, now what is my CL? CL, this is from your elementary, okay, CL alpha lift curve slope times the angle of attack. Now, if I substitute here this value CCL, I will get CL alpha into theta is the which input minus phi is up over ut, okay, into dr, okay. This is the approximate expression. Now, you see this is much easier if I write it, I take the half rho C ut square I take it inside. So, you will have CL alpha ut square is omega r theta minus up ut, okay. All right, and up you know v plus nu, ut is omega r. Now, it is easy for me to integrate along the radius. On the other hand, if I put divided by omega r and every other factor I do not take it, you know, it is going to become a messy stuff, okay. That is what is done first. Now, this is my lift for an elemental length. If I want the total, I go back. So, I erase this part, okay. Total thrust is total lift that acts on all the blades in the rotor system. That means, I assume every blade in hover behaves the same way, okay. That means, I will simply put number of blades n, all right, and then I have to integrate from this expression. I will put 0 to capital R, the entire expression you write this, you will have the full expression, which is maybe I will write this, then I will do the non-dimensionalization, because that is important, okay. So, you will have this is n 0 to R half rho C CL alpha omega r whole square theta minus up is V climb plus nu and ut is omega r into dr, okay. This is my thrust, rotor thrust. Now, usually we non-dimensionalize the quantity, we do not carry this whole thing. When we non-dimensionalize, we use I erase this part here, velocity quantities are normalized with respect to tip speed and you use omega r. So, you see Ct is thrust coefficient is thrust divided by rho pi r square, this is the area of the rotor disc, and omega, okay. This is my Ct. Now, I divide this entire quantity by this, okay. So, now please understand one thing, density card can vary along the blade, okay. But if my today most of the rotor blades actually they have a constant card except near the root, okay. Otherwise, your card can vary, because that is what your small model card is varying. So, you cannot use the same expression, you have to put that integration. But normally what is done is we take some constant card etc. and then we calculate. Now, when I do this, I get a quantity, I will just briefly describe, I will have n 0 to r. So, I am going to divided by rho pi r square omega capital R whole square, okay. This is what I am dividing. When I divide, let me write the expression here, okay. Ct I will have n, there is a half factor outside, anyway rho will cancel out, okay. Now, omega r whole square, you take it here. When you take it here, this will be omega square will go of r bar square. We write it as, I will say integral, leave it, it is essentially 0 to 1 it will become, okay, because pi r square is there, okay. There is a c, there is a dr. So, one of the r you take it to this, that will become r bar. So, I will make this bracket here, this will be d r bar. R bar means r over r, so integral is 0 to 1, right. Now, inside quantity, let me first write it, that is r bar square theta minus, I am going to call this symbol, this Vc plus nu over omega capital R by a new symbol which is lambda. Lambda is inflow, okay. Please understand this includes climb and induced velocity, okay. Later I may split this lambda c and then nu, some lambda I, okay. But right now I am calling it as lambda because this itself you can write it as lambda c plus lambda I. That means, sorry, c is climb, I is induced. You can split, that is later. Right now we will take it as lambda and one omega r gone, another one lambda r bar, okay. So, this is gone. Then you are left with pi r, okay. So, I can have here, there is a c and okay, because there is a one of the r has gone to r bar. Now, if you assume it is a constant card, okay, then you can take out the constant card means c also outside. So, I will take the c outside. Now, this quantity I am going to call it as sigma, which is essentially blade area, okay, over disc because if I multiply r and square, this is CR is card into span, that is the blade area, n is number of blades. So, because please note all blades are identical. So, you will have sigma blade area over disc area, this is called solidity. Okay. Solidity ratio, okay. Now, I can write this entire quantity as sigma over 2, okay. And then there is a CL alpha I have to add. So, CL alpha is there, sorry I forgot to put that CL alpha because this is there, okay. And CL alpha you may call it CL alpha or sometimes we call it A by the symbol CL alpha or A, both mean the same, okay. Now, you are left with completely this solidity ratio is important, usually blade area divided by disc area, okay. And this is an important parameter, like you have thrust coefficient. Now, we have introduced one more new quantity which is the solidity ratio of the rotor, because that plays a key role. As we go along you will see, okay. Now, this is what my expression for Ct. Okay. Now, this is the lift, it acts, please understand. Now, I go back here a little, we made some approximation. What is my lift? Lift is normal to the resultant flow, right, and drag is along the resultant flow. And I said in my hub coordinate system, x is in the plane of the hub, z is normal to that. I should take, if I want, actually the force normal to the rotor disc or the hub. I must resolve these two components L and D along vertical and this x direction, that is a precise. Now, I go and do that. I have written here normal force Fz is L cosine phi minus d sin phi, because that is a, you subtract, because this is the resultant is coming here, this is omega r. So, you have your L, your, I think I should, okay, this is L, this is D, and this angle is phi, this angle is phi. This is we said x, this is we said z. So, L cos phi minus d sin phi. So, I must drag also into account. And then in plane force is L sin phi plus d cos phi. Now, I make another approximation, that because my phi is small and the drag is usually for a aerofoil is very small, okay, it is, you can take it at the most 0.01, whereas lift CL is CL alpha, that is 2 pi. So, you say my drag is very small, therefore, Fz, please understand, Fz I say is L directly, okay. Now, that is what I have used only L in defining the thrust coefficient. That means basically this is normal to the rotor disc, that is all. This is the approximation, I make this. But in the case of a in plane force, I say Fx, I can't neglect lift, lift is large, phi is small. So, I am going to write it as L phi plus d, okay, because phi is small. So, cosine phi I take it as 1, sin phi I call it as phi, whereas when I go here d is also small, phi is also small. So, product is much smaller. So, I neglect that, whereas when I come here I do not do that. So, this is the, now you understand, right at the beginning I make all sorts of approximations, okay. That is what I have given here. I put it on elemental thrust, because this is just to indicate to you what all we have done. L dr, L is lift per unit span, this is dr, here I have modified slightly, and then n is number of blades. dt is actually thrust, which is Fz, okay. This is per unit area, so I multiply by dr, is it clear? And then when I go for torque, because I am not interested in the drag force, I want to see what is the torque, because drag force I won't just integrate it, I will integrate and then get what is the torque required to rotate. But later if I want hub loads, I need to get the drag also, I will do that later. but right now I am calculating only the torque is L phi, because I have approximated Fx L phi plus d, and it is acting at a distance r from the center. So, the drag force into distance is elemental torque, okay, and the power into omega, because torque into omega is power, okay. Now, I have all the three quantities: elemental thrust, elemental torque, elemental power. I have only shown you this particular thing. If I integrate this, okay, before I let me write the expression. Ct is, here I put what? Sigma. Now, Cl alpha, what type of airfoil you are having at every section, okay, whether it is a constant, because it can vary, because we said card is a constant, but my airfoil can change, but we make again, no, I am going to have the same airfoil throughout, okay. Now, Cl alpha also comes out, which I call it as using the symbol A, because most of the helicopter literature, they use the symbol A, okay. Lift curve slope, Cl alpha is A, sigma A over 2, 0 to 1, r bar square theta minus lambda r bar into d r bar, okay. This is my Ct, which is the non-dimensional, actually the first expression dt is there, right. If I integrate the dt over r, I will really, this is the thrust, that is normalized, I get this expression, okay. Now, how my theta is varying along the blade? I said pilot gives an input, that is the pilot input he gives at the root, but the blade itself can be twisted. That means there can have a pre-twist in the blade, geometric twist. That means what initially pilot gives, and then what is the angle, and as it goes what is the pitch angle at every cross section of the blade, that you have to take it. Now, here only there are, if it is constant, constant means there is no twist, 0 twist. 0 twist means you can directly take it, okay. If you integrate, it is very simple. Assume 0 twist, okay. Theta is a constant everywhere. This is very simple. This is what Ct becomes sigma A over 2 theta over 3 minus lambda over 2, that is all, okay. Very simple expression, but you do not know lambda, that is a different thing, but if it is hover, we will see how we get it from. If you have a twist built in the blade, then you have to take that into account. Usually rotor blades, they do with a linear twist, okay. Linear twist means the angle theta varies linearly from root to tip with a reduction. So, you can write it in a form where you have a twist, then you can integrate fully, okay. Now, why do you give twist? That is another question. So, you can have, but then the proof for twist, if you give, you vary your inflow also. There is a little different, because we still have not obtain this value, please understand. If you use momentum theory, assuming hover, okay, I am just going a little, only with this I am discussing, I have not gone to the other two terms, only this term. Zero twist, I am considering hover, then lambda becomes lambda I, that is all, induced, because there is no climb. Then I will have my Ct is sigma A over 2 theta over 3 minus lambda I over 2. But momentum theory hover gave me what? Lambda is root of, right? Sorry, lambda I should use the symbol lambda I, because this is for hover. Okay. Now, blade element theory is relating pitch angle, induced flow, solidity and airfoil characteristic, because all these are there. Number of blades, actually these are non-dimensional quantity. If you want, then operating condition is there, angle of attack, everything is there. Now I can substitute for lambda I here, okay, and then I can get theta, okay. Directly what should be the pitch angle I must give if I want to have this much Ct, okay. Then once I know the Ct, I can get the inflow. On the other hand, in an experiment, if I give a pitch angle, I must know what should be the Ct. That means I have to do iteration, because first I assume the value of theta, then I do not know this value, okay, I may take it as 0, you follow. Then I put the value of theta, I get a Ct. When I get the Ct, I go back and substitute here, then I get the lambda I put it back here, then I get the new value of Ct, go back, do the iteration. That is in a wind tunnel test. If you want to correlate, hey, I have given this much pitch angle, what is my thrust, okay, because these tests are done, lot of. So you see only these two equations, you are using only these two. Now in helicopters, you understand that you cannot live with only momentum theory, or you cannot live only with blade element theory. You can replace the momentum theory by some other theory, vortex theory, but this is essential, blade element theory is essential. So you always have two theories, either you say I take prescribed wake or free wake, any analysis, and then I get the inflow, then use that inflow, put it here, get the thrust, then go back again to see whether that thrust gives me that inflow, okay. Now you see the loop of the calculation in just a very simple problem. If I give you a weight of the helicopter and the rotor radius, some CL alpha, airfoil shape, etc., calculate what should be the pitch angle, you should be able to do it, okay. Now I will just compile this stuff and then write it here. Later we will see the twist part, right now untwisted, okay, 0 twist. So I have Ct and 0 twist and hover, please understand, because I am doing both. Ct becomes sigma A over 2 theta over 3 minus lambda I over and lambda I from momentum theory is root of Ct over 2. Now, I just want to, this is for practical purposes, you substitute this here and then collect the terms of Ct on one side, just in this expression. If you do that, you will get what? 2 Ct over sigma A, this is theta over 3 equals, this will go here plus 1 over 2. So, I take the 3, please understand I am taking the 3 here and put it 6, okay. Zero twist, hover. If I know the thrust coefficient, please understand, if I know the thrust coefficient, that means I know Ct, thrust coefficient I know, because that is the weight of the helicopter. Now you see, I do not really thrust coefficient, I equate to, sometimes people say weight coefficient. Basically weight is supported by the thrust, you say thrust coefficient is equal to Ct equal to Cw, please understand. So, I use this approximation again here. If you are given a weight of the helicopter, if it has to hover, W you say that is T, that is all, weight is equal to the thrust. So, you will have Cw is Ct, weight coefficient, thrust coefficient. Weight coefficient is nothing but W by rho, again pi r square omega r whole square, okay, which is same as if you are given a helicopter with the radius and with the rotor angular velocity, you can get the Ct. Now, you see what should be my pitch angle? I must provide for hover, okay. You substitute the value here, this quantity, you know that A, which is the lift curve slope, is theoretical value is 2 pi, okay, theoretical value is 2 pi, which is almost close to 6. So, you knock this out. Now, you see Ct by sigma, this is the mean angle, this is the term due to variation in the, because of the inflow, because of the inflow there is a change, okay. Ct over sigma, now please understand why this parameter becomes important. Thrust coefficient over sigma, this gives you mean angle, okay, approximately straight shot, because sigma takes Nc over pi r, Ct is thrust coefficient. Now, you will immediately say, hey, what should be the angle I must provide for hover, just mean value, this you, if you take it, it is okay, if you neglect it, it is all right. That is why in practical situations, helicopters, they always want Ct over sigma, what is the value, because that tells you what is the angle you must provide. Suppose if this value becomes for the aerofoil 15 degrees, then it is you are nearing stall, okay, of the blade, okay. So, it gives you, hey, do not go, you immediately see if I increase my solidity ratio, I reduce the angle for hover, that means my aerofoil is good, but if I reduce my solidity, I am actually increasing my angle of operation, but you may stall. So, these are very important, you have to operate, and if you are near the stall angle, if you want to climb up, because this is for hover, if I want to, I have to increase my thrust, I increase my collective, but what will happen is you will not be able to lift, the blade will stall. So, this is very important, CT over sigma as a parameter. Okay. This is also called blade loading. Okay. Why it is called blade loading, I will briefly describe. Because CT is what, okay, let me erase this. Okay. Why it is called blade loading? Thrust divided by rho pi r square omega r whole square. This is CT. Sigma is n okay. This is sigma. Now, this factor you can reduce it in a slightly different form, and which will give you approximately in a different form of expression. That is, I am writing it in this fashion, because if you take it as NCR pi r square, what happens? This will become pi r square will go off. Okay. This will become thrust divided by n number of blades CR, of course omega r whole square and rho. Okay. This is basically for non-dimensional stuff, but NCR tells you the blade area. Okay. So, this is also called CT over sigma is called blade loading. Okay. See, you saw disk loading. Disk loading was T over A. Then you saw power loading. Now this is blade loading. It also tells you how much each blade lifts, how it is shared by, how the load is shared by the blades. So, you see two non-dimensional parameters giving you the pitch angle of operation of the blade in hover. That is the critical thing. Now, I want you to note down, because this particular quantity, okay, you may call it blade loading, you may call it just mean angle of attack, whatever it may be. Mean angle of attack, actually mean pitch angle you may call it. I think I would better, mean pitch angle would be a better, okay, mean pitch angle required for operation. How this value, please understand, this is just for you to know, we are talking about hover. How this value vary with forward speed, okay, the limits, because we know it is related to pitch angle. Pitch angle means if you keep on increasing your CT, I am giving you one rotor, everything dimension, everything is fixed, operating condition is fixed, omega r is also known. But you keep on increasing the weight of the helicopter, what you will do? You have to keep increasing your blade angle. Up to some blade angle you will lift, after that blade will stall. That means you cannot lift more weight. That means that sets the stall limit, in the sense the limit that rotor can lift, beyond which that rotor cannot lift, because you have exceeded that. Now, this is true for even forward flight, but in forward flight also you have to lift the weight, in addition to overcoming drag, etc. Now, industry requires this CT over sigma. It is not a constant with forward speed, please understand, this varies with forward speed. Okay. This is the what I gave you as a project, because this is a very tricky stuff. Limit of the rotor, okay, I design a rotor, how much you can take it, because this is very important. If you are making, you cannot just like that take a rotor and put any weight. They have to make sure what is my operating condition and then I have the envelope well set. So, CT over sigma plays a very, very important role in the helicopters, okay. That is why I am saying, and this quantity is not, when I say blade loading, you tend to get an idea that, hey, you know the weight of the helicopter, everything is known, that means it is a constant, you will say, okay. Please understand, it tends to give you a feeling that it is a constant. That means irrespective of the flight condition, okay, it is a constant. But normally using this quantity, you define a limit, okay, with respect to, I will just draw the diagram, but I will not. CT over sigma, this is speed, forward speed, okay. Hover, yeah, I know that. That means how much this quantity in hover you can go for a given rotor. Please understand, this is drawn for a given rotor. Given rotor means sigma is fixed, right. These quantities are fixed, even rotor omega r is also fixed, but this you can keep on increasing up to a point where blade will, the angle you will reach such that the blade will stall, okay. And the same thing can happen at every forward speed, because every forward speed you will find I can keep on increasing the weight till the point where my blade will stall. That means that becomes your stall limit, it will be something like this. It may actually come down, 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 that means the limit you can go, it is drawn in CT over sigma curve, okay. But these are, actually I had a long discussion with HAL about this particular thing. Finally we figured out, this is the key, because this becomes important. But how do you generate this curve theoretically? That now we are going to do it, but we will give, because this requires a very detailed, if you want actual helicopter thing, but in a preliminary thing we can do simplistically, okay. So this is just for you to know CT by sigma is also used for drawing a limit of a rotor, stall limit you may say, okay, because beyond which if you go, blade will stall, you cannot, the rotor will stall, you may call it, rotor may stall or blade may stall. So it may come and hit like this if you say, okay. You see, if I go, I am stalling, because I increase my CT by sigma gone up, pitch angle is gone up, blade is stalling. Same thing will happen at every forward speed. But how do I get this curve? In forward speed with all complexities, that is the key. And they make sure that when they design the helicopter, you are always below here, you do not go anywhere near, because you know, because you never know, at some operation you may stall, and if you stall, loads will go up. And actually you, I do not know whether you people know, there were a couple of accidents, okay, which came in the video and other things. The pilot was doing a turn, and usually you go, you climb, but when he started for climbing, he was actually going down. Climbing means what? You increase your collective, you increase the collective, but he was going down, which means what? Blade has gone into stall. So these are very critical things. In maneuver, suddenly you may stall, and then you think that, because the pilot is, that is why it is very, very tricky. Of course, he walked out of the accident in one case it was a fatal, okay. So these are very important parameters in the helicopter field, okay. Now let us go to the next factor, which is the basically the torque part, and I will also give you a little bit of this twist. Before I go to the torque part, I will give the twist just directly from here. I am not going to write it, because this is just for if I have a linear twist, okay, linear twist, please understand here I use 0 twist. If I have a linear twist, theta naught, that is what is the value, theta twist into r over r, okay. This can be written in terms of the angle at 0.75 r, okay. .75 r. If you take it in this fashion, okay, please understand, if you take it in this form and put it in the integral, okay, and then integrate, you will get the expression like this, which is, I use lambda, it is exactly same. You follow? Please understand, if I take 0.75 r as my reference angle, okay, I am representing theta equal to theta 0.75 into r over r minus 0.75 theta twist, okay. This is fine, this expression is basically same as this, okay. I am putting it in a different form, okay. If I use this expression in my thrust and integrate, okay, this you can do yourself because you do it as a exercise, okay. If you take this expression, integrate, you will get this expression, which is essentially sigma a by 2 theta by 3 minus lambda by 2. Now you see theta represents the angle at 75% r, okay. So why is 75% is so critical? You know, most of the times we say because that is where the lift also becomes high, around that region, because near the root lift is small, then as you go towards the end the lift will rise up, and then of course at the tip it will drop, okay. We will come to the tip etc. later. Right now r, if you directly use this expression, you will have this, because you see if you take the 3 out, theta naught plus 3 by 4 theta twist, that is nothing but 0.75 angle at 0.75, okay. So the 75% of the blade is always, they will say what is the angle, you know, theta. Now there is something called a ideal twist. I will just mention this and then we will close. That is, if my pitch, please understand, r over r is in the denominator, tip angle I set, as I come inboard it will go like this, ideal twist. Linear twist is straight line, so it will be, that is theta, and linear twist may be like this, r over r, this is maybe 1, okay. But ideal twist, this is ideal, this is linear. You can't make it, okay, because you know, where how will you take it to infinity? Twist to infinity has no meaning, but up to some 0.2 radius, because near the root it is all not an aerofoil section. So you can cut it out somewhere here or someplace. Then you say, I can do something like that, I can manufacture. So you see, this I will give you as an exercise which you can try. I can have a ideal twist, okay, and if I use this, my CT will be this expression, sigma a over 4 theta tip minus 4. Expression is different. Now you see, depending on the twist, the expression for, now why ideal twist is in this form, but why do I call ideal is another question. The reason I call it ideal is, if I use this twist, my inflow will be uniform. I can prove that using another, again that theory we have to come. Whereas in all these things I assume that inflow is constant everywhere. Please understand, I assumed inflow is constant, but I do not know whether it is constant or not. That means I said lambda I equal to root of Ct over 2, I assumed it, but it is not true. That means I am making, even in this, right at the very simple expression, I am making a error. I assume this is constant, but I do not know whether it is really constant or not. Okay, this is a problem. You can use that, but you make errors. Now you say, how do I, later we will do, now the torque part we will do it in the next class. Okay.